the third thing is called a hash. A hash obscures text. It does not encrypt. Okay, this is not reversible. Okay, a hash. So I'll show you a hash. Here's the hash. What happens with a hash? Algorithm. You may have actually seen these already. A hash is a way to represent a value without storing the whole value. Okay? So let's say I have a customer database, and I have the customer state. Okay? How many letters does it take to represent states? Like, what's the longest state? Oh, no, we're not going to do 2 letters. We're going to spell the whole thing out. 2 letters would be easy too. Okay, we'll go with Mississippi. M-I-S-S-I-S-S-I-P-P-I. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, we've got a list of customer states, and it takes me 11 characters. If in my database, it would be like this, like CHAR 11. You guys ever done a database where you define your database? So I need to reserve 11.
This is from Jim Tyler. Technically, New Hampshire is 13 characters long.
Thank you very much. New Hampshire. That's what I get for letting you guys guess. By the way, this is what gets you. You'll predict like someone's last name. It'll be like, yeah, I think the longest one is 15. And that you're just begging for someone to come along with a 25 or something. So New Hampshire is 13. So I can reserve 13 characters in my database. If I hash them, though, there's only 50 possible values. So I'm going to do some sort of data representation. And I'm not going to get into how these work because it's just as complicated. Data representing. You write some, there's an algorithm you write, and you might end up with a hash that is, how many bits do I need to do 128? I could do 64, right? That's 8 bits long. I end up with a hash of, let's say, 8 bits. No, that's 256, all right. And what happens is I run my characters through this hash, and so it looks at the binary representation of the N, the E, the W, everything else. When I hash it, I will come up with a unique value for New Hampshire. So New Hampshire is going to be like 0110010 or 11, okay? Mississippi is something else. Okay, and so on. So they're all different. Y'all see that? So I'm using only 8 bits though, instead of 13 times 8. Follow me here? So by hashing it, I get a way to represent these other values. So far so good? So it's data representing the characters. So I'm taking the whole thing and hashing it. Okay, that's what a hash does, and it's destructive. Okay, the part of what did I put here? It's not reversible, not reversible. I already put that up here. So this is not reversible, remember. So if I go down and I find 011000011, I can't decrypt it and come up with New Hampshire. This 01100011 is the way I represent New Hampshire. We good here? Takes up less memory on my database. We good? And I can have a lookup table that looks it up. Yeah, it's not an encryption. This is what you use for passwords. We'll talk passwords in just a second. You'll see why. Okay, so this is what we do just in computing. Okay, if you index a field in your database, what it does is it goes through your table and it sees, what's sort of a good size index or hash value I would need to represent all the values in that thing. And then it creates this hash table, and then in memory it only holds the hashed values. On your disk it holds the hash values and the original values, so it can look it up. So you can get a fast search, right? Like on a key field, if I want to sort really fast, I can sort really fast the 8 bits, and then I can go back and put the stuff to them. Yeah, usually it's a whole field though. So you're saying would it look at the? Yeah, the would get its own hash, like obviously New Hampshire would. This whole thing. I can hash actually a whole file if I want to. And what there is with a hash. Mm-hmm. What you want is a one-to-one correspondence. Not one-to-one correspondence. Yeah, you do. What you want is to have what's basically called no collisions, or what do they call that? No. Dang. I lost my thing on it. No, it's the word that means if I did Mississippi and New Hampshire, I would never get two that were the same hashed value. Okay, we'll just call it copies. There's a special word for it. There's no way that they're going to repeat. Let's just go with that, okay? So this is the ideal. It is, well, I think they call it collisions, but I don't know. The ideal. So the ideal hash gives you a one-to-one correspondence. That is, for every original value I put in, I get a different hash. I should have just said that. I'm trying to come up with a fancy word. Every original value has a different hash. Okay? And that's important here, right? I mean, you can see that here. If, for example, I did New Hampshire and Utah and they came up with the same value, then I'm screwed. It doesn't help to do the lookup of the difference. All right, so hash. Now, a normal hash, let me make sure I told you there was a file that can be hashed. You can hash a file. And so the hash becomes what's called a checksum. You might see when you're downloading something, it'll say like MD5 checksum. And then it'll have this long string of letters. When you're downloading something, I can download the whole file, and then I can see if my checksum matches what the person said the checksum should be, and then that tells me I got the file intact. We good with that? So that's one of the things we use hashes for, besides just the savings on the memory. Now, we do it for well, let me just do. So, with a hash also, the any length of input produces a fixed length of hash, or it should produce. Okay, so if I put in, if I put in Fox, and in this particular thing, I'm going to get out, what have I got? 1, 2, 3, 4, 40. I'm going to get 40 bytes. And it's going to be something like, man, my getting old, DF CD, blah, 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 blah. Okay, so it's going to be 40 bytes long, and it'll have this. These are actually hex. It ends up being hex. Okay, so I put in Fox. It's only 3 letters long, but when it comes out, I have 40 characters out. Okay, it doesn't matter how long of a. It ends up being a point for the passwords, right? If I could put in 1 character for a password, I would still get these 40 bytes out, right? Even if someone had 16, it would still be the 40 bytes. And so you can't tell just by looking at the hash how long the password is. There was a while back when Microsoft did a hash and it was messed up. And you could tell if someone had a password that was less than 7 characters, or 7 characters or less. That was awesome. Because then you could see like, oh, these are all less than 7 characters. And then there's an easier way to get them cracked. Okay. So if you do a longer one, so I put in the quick brown fox and I hash that, I'm still going to get my 40 bytes. Okay. But it's going to be different 40 bytes. So it's like, I'm not going to write the whole thing down. 86. Good grief. This is tiny text. 46 CB. Okay, blah, 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 blah. Okay. If I do a tiny change, the quick brown. That's kind of lame. They should have put box, because you change fox to box, right? That's all right. We'll just pretend that's what they did. So if I just change the F to a B, I get something totally different, still my same 40 characters, and now it's going to look totally different than those other two. B, F, C, D, 1, 7, E, 4, B, blah, 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 blah. Y'all seeing that? So a small change, any input produces a fixed length hash, and a small change gives a completely different okay? So that makes sense, or that you can kind of see the usefulness of it.